We saw in an earlier section that for every linear transformation, there exists a transformation matrix, which, when multiplied by a vector, can transform that vector to another vector. Nonetheless, there exists a set of vectors, which, when multiplied by the transformation matrix, do not change direction. The magnitudes may be changed. To be more precise, such vectors stay on the line they span out without getting out of the line. Such vectors, which are simply stretched or contracted when multiplied by the transformation matrix, are called eigenvectors, and the corresponding factor k by which they are stretched or contracted is the corresponding eigenvalue. So, if you want to stretch space in a particular direction, it suffices to choose the matrix of transformation such that the eigenvectors and eigenvalues will permit you to stretch space exactly as you want. Let's take an example to illustrate this. Say we have a transformation characterized by a transformation matrix for 2, 1, 3. Now, we could have the point 2, root 5, 1, root 5. This point can be transformed by using this transformation matrix. We could also have this point P2, which is 1, 0. P3, 1 on root 2, negative 1 on root 2. P4, 0, negative 1. P5, negative 2 on root 5, negative 1 on root 5. P6, negative 1, 0. P7, negative 1 on root 2, 1 on root 2. And P8, 0, 1. Notice that all these points lie on the unit circle. That is, if you find the magnitude of these points, you will find that all of them give a magnitude of 1. Let's take an example. Here we have 0 squared plus 1 squared, which is equals 1, and the square root of 1 is 1. 2 on root 5 squared is 4 on 5. 1 on root 5 squared is 1 on 5. 4 on 5 plus 1 on 5 is 5 on 5, which is equals 1, and the square root of 1 is 1. We could continue to all the other points. Now, say we want to transform P1. We simply multiply this matrix with P1, which is this vector. We have this matrix times P1, which gives us this other vector. Representing this vector geometrically, we have this vector at this point. Notice that the direction of this vector remains unchanged, as this point is found on the same line this vector spans out. Now, the only difference is that the magnitude of this vector, which is this, is 5 times the magnitude of this other vector. You can see this clearly by multiplying this vector by 5. 5 times 2 on root 5 is 10 on root 5. 5 times 1 on root 5 is 5 on root 5. And that's how we have this. So, this vector is an eigenvector. Let's move to the vector linking the origin and the point P2. The transformation of this point P2 can be gotten by multiplying the transformation matrix with the point P2, and this gives us 4, 1. Notice that this vector formed by linking the origin and 4, 1 isn't in the same line as the original vector linking the points 0, 0 and 1, 0. So, this vector linking the origin and 1, 0 isn't an eigenvector. On to the next vector linking the origin and P3. Its transformation leads us to this point 2 root 2 and negative 2 root 2. You can see already that multiplying this by 2 gives us this, and this by 2 gives us this. So, geometrically, it's found on the same line as the vector linking the origin and the point P2, or the point P3. So, we have that this vector is an eigenvector, while the magnitude of this other vector is twice the magnitude of this original vector linking the origin and the point P3. For the point P4, we have -2, -3. This means P4 isn't an eigenvector of this matrix Tm, since its transformation by Tm doesn't lie on the same line with the vector linking the origin and P4. And then we have got P5. For P5, the resultant vector is -10 on root 5, -5 on root 5. This vector is located on the same line with the vector P5. So the vector linking 0 and P5 is an eigenvector of the matrix Tm. Now, P6 gives us -4, -1, so we're leaving from this vector to this other vector, making P6 a non-eigenvector of this matrix. P7, -2 on root 2, 2 on root 2, which also lies on the same line as the vector linking the origin and the point P7. So this vector is an eigenvector of the matrix. And finally, we have the transformation of the point 0, 1, which leads to 2, 3. And we have this new point, which is forming a vector which doesn't span the line of P8, or the line spanned by the vector linking the origin and P8. So, considering this unit circle, we see that this transformation with this transformation matrix actually stretches out this unit circle 5 times in this direction and twice in this other direction. So, we see how this notion of eigenvectors and eigenvalues can help us stretch space in a particular direction. And in this case, space is stretched in this direction 5 times and in this other direction 2 times. And we have this eigenvector, which is multiplied by 5 simply. And that's what we have. Then this other eigenvector multiplied by 2. And this is what we have. It's important to note that this matrix doesn't only have just this as its eigenvector. Recall that when we were working with these vectors, the point P1 and the point P5 were both eigenvectors, and both of these vectors all lied on this same line. So we can say that the eigenvectors of this matrix are actually all the vectors which lie on this line, and also all the vectors which lie on this other line. So if we have a vector at this point, for example, and we multiply it by this matrix, it's going to be somewhere 5 times this vector. So we're going to take this vector and multiply it 5 times and get the magnitude, which will give us a vector far away, but of magnitude 5 times greater than the magnitude of this vector linking the origin and this point. And similarly, with this other line, we have, if we choose a vector at this point linking this origin with this point, we'll simply multiply this by 2, and we should be found around this point. So, for all x element of Rn, if x is an eigenvector, A, which is the transformation matrix, times x is equals lambda times x, where lambda is the corresponding eigenvalue. In this example, lambda was 5 for the eigenvectors which lied on this line, and lambda was 2 for the eigenvalues or the eigenvectors which lied on this other line. So this is the definition of an eigenvector. Now, when given a matrix, we shall see how to obtain its eigenvectors and eigenvalues. Since ax equals lambda x, we have ax minus lambda x equals 0, which is a minus lambda Rn times x equals 0. Notice that the identity matrix has been inserted, and this is because without inserting this identity matrix, we have a minus lambda, so we're subtracting a matrix with a constant, and that's not correct. But multiplying this constant by the identity matrix turns this part to a matrix, and now we have a homogeneous equation. With this, we have that if b is equals a minus lambda in, then this means bx is equals 0. And if there exists an x different from the 0 vector where bx is equals 0, it means this b has a null space which is different from the empty set. So x is part of the null space of b, with b equals a minus lambda in. From this we can say that b inverse doesn't exist. As for b inverse to exist, the null space of b must be equals to an empty set, and the column space of b must be equals the number of columns of the matrix b. So this implies b inverse doesn't exist, and when b inverse doesn't exist, the determinant of b is equals 0. So if the determinant of b is equals 0, this implies the determinant of a minus lambda in is equals 0. And with this, we can calculate the value of lambda, which is actually the eigenvalue or the eigenvalues when there are many other eigenvalues of the matrix. This equation is known as the characteristic equation of the matrix A. Let's take an example. Say we have this matrix A. Let's find the eigenvalues of A and their corresponding eigenvectors. We first start by finding the characteristic equation of the matrix. We have the determinant of A minus lambda I to re, since n equals to re, is equals 0. Finding the left side of this equation, we have this determinant of A, which is this, as we had, minus lambda times I to re. Now, subtracting, we have 2 minus lambda times 1, which is 2 minus lambda, 2 minus lambda times 0, which is 2, 0 minus lambda times 0, which is 0. Now, just notice that all we need to do is to modify these elements on the leading diagonal, so the rest remain intact. So we have 2, 0, 1, 0, 1, and 1. Then to obtain the determinant of this matrix, we can fix our first row since we already have a 0. With this, we have 2 minus lambda into the determinant of this matrix made of negative lambda, 1, 1, 2 minus lambda, minus 2 times this matrix made of 1, 1, 0, 2 minus lambda. Since here we have a 0, we simply ignore it, and we have 2 minus lambda into 2 minus lambda times negative lambda minus 1 times 1, and this is what we have. Then the next, we have minus 2 times 2 minus lambda times 1, which is 2 minus lambda, minus 0, so we just have 2 minus lambda. Notice that we have a negative sign here, and that's because when we add the row number with the column number, we have 3, and negative 1 to the power of 3 is negative 1, so we have to put a negative number here. Now, a quick way to look at this is we have 2 minus lambda, and here we have 2 minus lambda. So factoring out 2 minus lambda, we have this, and then we have this part minus 2, which gives us quickly this. And this is equals 2 minus lambda into lambda minus 3 into lambda plus 1. Now, coming back to the characteristic equation, we have that the determinant of A minus lambda I3 equals 0. So this is equals 0. And if this is equals 0, it means that we have 3 different eigenvalues, which are lambda 1 equals 2, that is when 2 minus lambda equals, lambda 2 equals 3, that is when lambda minus 3 equals 0, and lambda 3 equals negative 1, that is when lambda plus 1 equals 0. Now that we have the eigenvalues, let's go ahead to find their corresponding eigenvectors. When lambda equals lambda 1 equals 2, let's find x such that a minus 2 I3 times x equals 0. This is gotten from this equation we had earlier stated, where our lambda is the eigenvalue and x is an eigenvector. So we're finding this x which verifies this condition, and that's what we have. So a minus 2 I3 times x equals 0 implies that this matrix times x equals 0. Notice that to obtain this matrix, we simply come to this matrix we initially had, which was actually a minus lambda I3. So we replace lambda by 2, and if we replace lambda here by 2, we have a minus 2 I3, and with that we can quickly have this, and 2 minus 2 is 0, minus 2 is negative 2, 2 minus 2 gives 0, and so this is the matrix a minus 2 I3, and this x is represented as x1, x2, x3 equals 0. This 0 is actually the 0 vector. Now, we are actually finding the null space of this matrix a minus 2 I3, as we had seen earlier. So, we're gonna use the same methods we had used in other sections to find this null space, that is, values of x such that a minus 2 I3 times x equals the 0 vector. Rearranging this matrix equation, we have this other equation. Now, we'll try to put this matrix to the left in its echelon form. The first thing we can do is by simply swapping the row 1 and the row 2. So we have 1, negative 2, 1, 0, 2, 0. And once this is done, we can try to send this one to a 0. So we have R2 or R3, which is equals R2 minus 2R3. And that's because if we have this equals 2 minus 2 times 1, we have 0. So here we have 0, which turns to 0 minus 2 times 0, which is 0. And then we have 2 minus 2 times 1, which is 0. Here we have 0 minus 2 times 0, which is 0. Our matrix is now in its echelon form, so we can rewrite these equations as such. Now we have 1x1 minus 2x3 plus x3 equals 0, and here we have 2x2 equals 0. x1 is equals 2x2 minus x3, that's by sending these two terms to the right, and x2 equals 0. Rewriting this, we have x1 equals negative x3, and that's because x2 equals 0, so here this goes away. So we have x1 equals negative x3, we have x2 equals 0, and x3 equals x3. This implies that x is equals the span of negative 1, 0, 1. We gotten this by factoring out x3, which is a constant, and having negative 1, 0, 1. And that's how we have this. So this means all values of x can be written as a linear combination of this vector. And this vector is the corresponding eigenvector of this eigenvalue. Or these vectors are the corresponding eigenvectors of this eigenvalue, since there are many vectors which can be generated from this vector. When lambda equals lambda 2 equals 3, we shall find the vectors such that a minus 3i3 times x equals 0. A minus 3i3 x equals 0 implies that we have this matrix equation, and to obtain a minus 3i3, we'll simply replace lambda by 3. So we have 2 minus 3, which is negative 1, negative 3, which is this, 2 minus 3, which is negative 1, and the remaining elements of a remain intact. So we have this times x equals 0. We go through a similar method where we have to send this matrix to its echelon form. Notice that adding up these two elements gives 0. And so we have R2 equals R2 plus R1. And this turns this part to 0. And then to eliminate this one, we have R3 equals R3 plus R2, which gives us a row with all zeros. Now we've gotten the echelon form. So we have this resultant system of linear equations, which gives us negative x1 plus 2x2 equals 0 and negative x2 plus x3 equals 0. x1 equals 2x2, x2 equals x3, and we can have this with x3 equals x3, which is equals x2. Now factoring out x2, we have x equals the span of the vector 2, 1, 1, meaning this vector is capable of generating all the eigenvectors of the matrix. When lambda equals lambda 3 equals negative 1, we can find the eigenvectors, which verify a plus I3 times x equals 0. A plus I3 x equals 0 leads to this equation, which permits us get the null space of a plus I3. Now, rearranging or rewriting this equation, we have this, and we'll try to send this left side to an echelon form. Now, we'll leave from this to this, and then to this, and finally, from here, once we have the echelon form, we extract the system of linear equations. x1 equals negative 2 on 3x2, and x2 equals negative 3x3. So we have x1 equals negative 2 on 3x2, x2 equals x2, and x3 equals negative 1 on 3 x2. You could also rewrite this system of equations in terms of x3, where we would have x1 equals negative 2 on 3, and x2 is going to be replaced with negative 3x3. Then x3 or x2 equals negative 3x3, and x3 equals x3. But let's just do it this way. Now we have this, and factoring out x2, we have this vector, which actually forms a spanning set of all the eigenvectors. So with this vector, we can generate all other eigenvectors with eigenvalue negative 1. For our in-class exercise, we shall find the eigenvalues and the corresponding eigenvectors of these two matrices B and C. Notice that the C happens to be this matrix we had. So normally your eigenvalues should be 5 and 2, and your eigenvectors should be a factor of these vectors. So good luck on this, and see you in the solution. For the first matrix B, you should have repeated roots. So our polynomial equation is made of repeated roots, where we have lambda equals 1 appearing twice. So lambda 1 equals 1, lambda 2 equals 1, and lambda 3 equals 7. For lambda equals lambda 1 equals lambda 2, we have two vectors which generate all the eigenvectors. So unlike other examples where we just had one vector, in this case we have two vectors which generate all the other eigenvectors. So instead of having just one vector which generates all the other vectors on the line, in this case we have two vectors which actually generate a plane. So our eigenvectors in this case lie on a plane instead of a line. When lambda equals 7, we have this vector which generates all the other vectors which lie on a line. For the second example, we had this matrix which we had treated earlier, and we have lambda 1 equals 5 and lambda 2 equals 2 as expected. When lambda equals 5, we have this vector which generates all the eigenvectors on the line. Recall that we had 205 and 105 as eigenvectors, and we can see clearly here that multiplying this vector by 105 actually gives us the vector 205, 105. So with this vector, we can generate all the eigenvectors of the matrix C. Similarly, when lambda equals 2, we have this vector which can generate all the other eigenvectors. Previously we had 1 on root 2 and negative 1 on root 2 as eigenvectors, and we see that multiplying this by 1 on root 2 gives us that value. So we've seen how once given a matrix we can obtain the eigenvalues and their corresponding eigenvectors.